Welcome to Synapse. Imagine finding a distant world identical to our own in every way. Blue oceans shimmering under a familiar sky, green continents stretching to the horizon. It is the ultimate dream of space exploration, discovering an Earth twin located right in the habitable zone. The habitable zone is the specific orbital region around a star where temperatures allow liquid water to pool on a planet's surface. But a planet's location is only a fraction of the survival equation. Without a precise Earth-like mix of nitrogen and oxygen, or a robust magnetic field to deflect cosmic rays, that inviting sky is instantly lethal. Without the correct atmospheric pressure, our first breath on that planet would also be our last. Even if we find liquid water, the universal solvent for life as we know it, the climate could fluctuate wildly. A shift of just a few degrees could lock the entire globe under a shell of perennial ice, or fuel hyper-violent planet-wide monsoons that never end. Orbiting at the right distance from a star doesn't guarantee a welcoming home. It usually guarantees a raw, hostile environment. Any colonizing species landing there will face a harsh reality, radically adapt to the local physics, or die. Take gravity, for example. If a planet is denser than Earth, the increased pull changes the shape of life itself. Trees grow shorter and stockier with massive root systems to prevent collapse, while animals develop thick bones and heavily muscled bodies just to stand up. Drop the gravity, and you get the opposite: delicate, towering plants reaching into the sky, and wildlife capable of enormous, soaring leaps. Human engineering would have to follow these exact same rules. On a high-gravity world, our settlements would be wide, low-profile bunkers built from ultra-strong materials to withstand their own weight. On a low-gravity planet, we could construct slender, soaring spires that stretch into the clouds, topped with massive, lightweight domes. Then there is the local sun. Many Earth-sized planets orbit red dwarfs. A red dwarf is a type of star that is significantly smaller and cooler than our own sun, emitting a dim, pinkish-orange light. This completely shifts the entire energy equation for the surface. To survive under that dim radiation, native plants couldn't afford to reflect any usable energy. Instead of green, forests would likely evolve dark, almost pitch black or deep purple leaves, engineered to absorb every scarce photon of red light. The mass of the rock under your feet and the spectrum of the star above your head act as an inescapable evolutionary sculptor. They dictate the shape, color, and rhythm of life, entirely overriding the biological rules we are used to on Earth. And that assumes life uses the same chemical building blocks. On Earth, complex molecules like DNA rely on carbon, but on a different world, biology might run on silicon. Organisms based on silicon could develop leathery, glass-like skin, moving at a slow, glacial pace while consuming raw minerals directly from the crust instead of organic matter. This radar imagery of Titan shows dark lakes of liquid hydrocarbons, proving liquid methane oceans exist in sub-zero environments. Here, alternative biochemistry could thrive. Alien creatures might use freezing methane as a vital fluid, swimming where Earth life would shatter. For humans to survive alongside such ecosystems, we would undergo physical and cultural changes. Over a few generations, our skin pigmentation might permanently darken to block intense alien ultraviolet radiation. Even our culture would adapt to the new sky, forging mythologies centered around unfamiliar sights, like the eternal twilight of a twin moon system. Sustaining an interstellar colony depends as much on internal shifts as it does on external engineering. For our species to take root, human culture, architecture, and biology must align with the physics of an alien code. Astronomers are already mapping the starting points for this journey. Candidates like Kepler 452b, a world slightly larger than Earth orbiting a sun-like star, and Proxima Centauri b, an exoplanet located just 4.2 light-years away, are our most promising targets. An exoplanet is simply any planet located outside of our solar system. We are investigating these worlds right now. Using equipment like the James Webb Space Telescope, we scan their distant atmospheres for biosignatures. A biosignature is a chemical indicator, like a wisp of oxygen or trace amounts of water vapor, that strongly suggests the presence of biological life. But finding a target is entirely different from reaching it. The cosmic distances are so vast that with our current propulsion, the trip would take tens of thousands of years. Crossing that void requires either massive generational ships, where entire families live and die in transit, or placing crews into deep cryogenic stasis to sleep through the centuries. If a crew does survive the journey, the descendants who walk out of those ships will no longer be strictly Earthlings. Separated by light years and physically sculpted by new gravitational pulls and foreign stars, these colonists will slowly evolve into a distinct new branch of the human family tree. Crossing the void creates a permanent split in the human story. By settling another world, we surrender the specific landscapes and skies that defined us, eventually looking up at an unfamiliar night to see the cradle of humanity reduced to a single faint blue dot.